Hi everyone. This is ME 5390 Advanced Thermal Design. Today I'm going to continue discussion heat exchangers. Last time I think we discussed circular Findechou heat exchanger, and today I'd like to move on the most effective heat exchanger, which is called plate fin heat exchanger. This is the best heat exchanger so far, as far as I know. Okay, so we like to look at it. The in order to have the most effective heat exchanger, the offset strip fins, OSF, is adopted. So, and okay, so let's look at it. The gas to gas, something like that. The plate, fin, heat exchanger, cross flow, heat exchanger, and the so compact. Okay, so compact, and to increase the heat transfer area, offset fin. Look at that. There's something we call the wave. It's not really wave, but something like that. So that so many area, heat transfer area, both gas, so whatever, air, one side gas, the other is air. Particularly fuel cell power plant, the inlet air temperature is increased using the out of the exhaust gas. So one side is gas is coming out, the fresh air is coming. We like to obtain the waste heat recovery. So that this is so important in fuel cell power plant. And this is a the power plant is running over the years, and effectiveness is so important. Okay, saving money. So the government, solicit the research project to improve the effectiveness many years ago. So many university research laboratory, they are looking at, they thought that this is one of the best, this type, offset strip fins. So what, if you look at well, actually, it's a repeat. The pattern is repeating, and so we can look at the structure of straight fins, something like that. And then this is offset straight fin inside between the plate and when we look at this is unit shell. So we look at unit cell. So once we figure out the unit cell, and then it's a repeat. I think symmetry. So how many unit cell per between the plate and how many flow, something like that. So we can figure out. So basically unit cell. So this is turns out unit cell. I think if you carefully look at it, the plate the thickness is delta W war, and the fin, actually this is the continuous fin, thickness is delta, we call, okay, delta, and the each flow, um, the is like a fin. Look at that. It's not complete, but the fin and something like that is a profile length. Something we use a concept of fin, something like a profile length. So B1 for one fluid, B2 is the another fluid, whichever the hotter, maybe exhaust, is subscript is 1. So cold fluid like air is a subscript 2, something like that. So and then the each pitch of the fin P of F we call this is actually center of a fin. So we define the pitch PF, and then this distance is B minus delta. Obviously, this is delta. Okay, look at that. This is so we define the thickness and the PF, and well, actually, in order to figure out the heat transfer area, open. So what is open heat transfer area? Is shaded. I think you have to have some speculation. The shaded is open. Shaded is open. But the cross shaded is not closed. It's not open. So if it is not open, we don't consider as a heat transfer area. In order to have a heat transfer area, it must be open, and the gas flows and convection heat transfer coefficient, something like that. That's so obviously, if you look carefully, it is a repeat fin is repeating, and the offset and something like wave also, you know, wave. It's not exactly wave, but so that this must be closed. These two area considered close because it's a touching with the next offset. Okay, so we don't consider open. Otherwise, it is open. So each unit cell, the shaded is open, considered as a heat transfer area. So many heat transfer area. So and we say L1 for gas, hot side. Say gas. L2 with us because this is a cross flow. L3 is height. L3 is height. That's the dimension. So the L3 is we can define L3 is dW, the wall, and the number of pass. Okay, this is one pass. Well, actually, it turns out there are one more pass. So just plus one dW, and then B1 is the number of pass, and then B2. Why we considered B2 L3? Yes. If you look at carefully, there is a B1, but also the thickness of B2. You know, so not only B1 but B2 and the thickness. So that L3 consists of B1 number of pass and the B2 number of pass. The other one should be one greater, more than one. And then thickness. Actually, there is a thickness of wall. So that's the total length, height, L3. I think you can, if you have a question, you can raise a question. But as long as approximately understand, that's fine. Okay, it takes time. So once we have that, then we can, because NP, we can figure out NP, depend on the height and profile length of fluid 2, thickness of wall, B1, B2, something like that. That's what we found. Okay, something we move on. So and then number of fins. Number of fins is L1, one side, and then pitch. L1 divided by pitch, but also there are a number of passes, something like that. So it appears very complex, but if you figure out the unit cell, then one by one, you know, this is fluid too. It turns out one more geometrically. So and then primary area. Total area is the primary area and the fin area. So primary area, you know, primary area is except the fin. Okay, fin is fin area. Look at that. So fin area except the cross, you know, shady. So as I mentioned, we just take account all the fin area and then primary area and offset number, how many offset, fluid 1, fluid 2, L is a wavelength, say, okay, because of offset. We call wavelengths, assuming wave. So I think forgot the wavelength is the length of I believe the offset, one offset wavelengths, L2, L1, whatever. So that we define number of fin, yes. So total is primary and the fin, and the cross flow also we can figure out. Cross flow. Cross flow is a flow area. The flow area, the flow cross flow area. Okay, we can figure out. So as long as we can figure out the cross flow area, and then a frontal area is L1, L3 frontal area. Now again, the hydraulic diameter is again usually hydraulic diameter is 4A of perimeter, but we multiply L1, L2, L2, so that it become a total area of 4A cross flow and L2, something like that. Okay, so we can figure out a hydraulic diameter, and we define fin profile length. The profile length is we have to figure out actually. So B1 divided by 2, B1 is so I think what was a B1? Yeah, B1. Look at that. The B1 divided by 2. The fin is half of it. Okay, half of it. This is the fin, and divided by minus delta also. I think so. Reasonably, we define the profile length. B1 divided by 2 minus delta. That's a profile length. Okay. So once we have a profile length, and then using the fin theory, once you consider fin m value, we just, and then efficiency, we can hyperbolic tangent. You remember m. Because B is taken, so I use LF profile length because B is used. So that overall, because so many fins. Wow, once we have that, and then there is a correlation of look at that for J, Coulomb factor, and F, friction factor. We found some empirical correlation, and I compared, Usually, I'm very careful. I don't want to just use a correlation myself. This is my work. There was a correlation, Corbin factor, a friction factor, from Mengelink, Berger, with experiment, Case and London. Wow, look at that. The marks are Case and London. It turns out a good agreement, Reynolds number and Corbin factor or something. So we're gonna use this in our this is hydraulic is a approximation. No, this was we found, so we can use it. Now, once we accept that, then we can compute plate fin heat exchanger, gas to air, single pass cross flow heat exchanger is contemplated for heat recovery from exhaust gas to preheat incoming air. I told you in a fuel cell power plant. So some dimensions chosen, fin thickness is chosen, and plate thickness and the fin density, fin density per meter, and space B1, B2 is given. Offset L1, L2 is given. Offset. And then asking, determine total heat transfer and the hydraulic diameter in this example. Okay, pressure drop is very challenging. We can do that, but in this example is a total heat transfer, hydraulic diameter. Okay, so let's look at it. Property, what was the inlet? I think we read it. There's information. Offset the strip geometry employed on gas air side, properties service given. Those fins and plates are made of some, because of temperature. This is a very high temperature resistant material, stainless steel, something 625 K is given, thermal conductivity, plate thickness is given, and the temperature, gas flow rate, volume flow rate was given. 900, wow. 3.494 cubic feet per second, huge. And then air is 1.3 and 200. Well, this is exactly the government provided for fuel cell. Okay, research project, and then inlet temperature is 160 kPa. Air is 200 kPa inlet. Okay, actually we can calculate the pressure drop. And the property of air for gas can be used. Okay, gas is very close to air. It's a little different, but so that now gas is 2, 1 hot. Inlet is 400, outlet is we don't know. And then air inlet is 200, outlet is we don't know. We don't know, but we have to assume 400 and 600 and then calculate, not to calculate property tables. Table A2 and for gas and air subscribe and thermal conductivity of a fin is given, and the T high temperature one inlet is 900, outlet is a cold inlet is 200. Inlet pressure was given, is a given information. Volume flow rate is given, and the gas constant is assuming air, and then density calculated using ideal PVRT, ideal gas. This is same as because specific volume is 1 over. So I can compute the density using pressure and the temperature. That's what I did. Look at that. So inlet is density is calculated. Problem is outlet is very, yes.
For the density, should we, so you want us to use the ideal gas law and not table values?
The table value is very close to this.
Right. I just was kind of wondering because like with the homework, there was as the outlet density and stuff, or the inlet density. I used the PVNRT, but it was also
Yeah,
like
anyhow.
yeah, there's density there too. There's the table value. So they are off by like 0.2, but
Yeah.
I just didn't know if we
Um,
should use the ideal gas law then.
yeah, I think this is a table is they don't. It's a very atmospheric.
Right,
So
right.
this is not the good.
Okay. So
So
use, okay, I see.
because of pressure, we have to use this.
And
You
is
know.
there a table in the book for the gas constants?
No,
We
we
have to,
assume air.
okay. Well, I just didn't know if there were going to be any other like,
Yeah, could be, but just use
okay,
air property in
okay.
this problem. Okay,
All right. Yeah.
possible. If you know exact, then might be a table. It's not available in this book, but yes,
Right. Okay. Thank you.
yeah. And then mass flow rate is once you have a volume flow rate, then you can calculate the mass flow rate. And L1, L2, L3 is given, okay, in this problem. So that I can use it. And then thickness, this is fin, this is wall thickness, and this is pitch. B1, B2 is the same. Lambda 1, lambda 2 offset stream length is same. And then I calculate using the number of paths, just using equation. Just move on. If you look at, and then I can calculate the primary area, 1 and 2, same, almost the same. Look at that, 28. And then fin area, uh, almost the same. There's a slight difference because the number of paths is different, but anyhow, the same. And then total area, look at that, very close. And cross flow area is very close also. And then hydraulic diameter, wow, look at that. the dimension is 1 meter, 2 meter. Hydraulic is 1.5. So compact. You know, this is a 1 meter, 2 meter of size. The dimension, 1 meter height is so compact. We calculated hydraulic diameter. Sorry. Yeah, that's the example. But we can continue the in terms of mass velocity and the Reynolds number, and then calculate the Coulomb factor and the friction. Once you have that, then you can calculate the H1, H2 convection coefficient. And then using M fin theory, I can calculate the efficiency. Ooh, 0.8, overall 0.9. So compact, so good, actually. Because dimension was given, that's the way we have a high efficiency. And then the area, and then UA calculated, and using effective NTU method. So CL and NTU, because this is cross flow, I think both fluid unmixed. No, there's no way mixed. So you will use this is given. Effectiveness, oh my goodness, 0.827. Huge effectiveness, because effectiveness defined is Q max possible over actual. Amazing. You can $1 billion saving in a year. I'm sure if you have this kind of good effectiveness power plant. So and the outlet temperature, it turns out 320, 700. It's a little off. We assumed 600 and 300. I think this iteration is okay. Otherwise, you have to repeat. Now, the problem is a pressure drop. Pressure drop is we use the effect of a contraction, effect of expansion. You remember. But the problem is density is so complicated. P1 is okay. We calculate, and 1 is okay, but 2 outlet is once we have temperature and the pressure, yes, we can calculate. So that mean and porosity and the pressure drop this is a pressure drop, so important. That the pressure drop is so important, pressure drop, to estimate. Once we have a pressure drop, okay, so pressure 2, and then outlet pressure temperature, we figure out. Okay, now the what I'm thinking is, first of all, homework is for, I think, 13 homework. For practice. I'm thinking midterm 2. Okay. So midterm 2, we will discuss after break. I like to have a break a little today and then talk about midterm 2. Okay, about 10 minutes break. Hi, I'm back. Let me- Page is 315. Yeah, heat pipe. This is a page in the textbook, 315. Plate, finned, heat pipe, heat exchanger. Okay, heat pipe. This is interesting. Something like that. Okay. There's a heat pipe and gas or hot gas. Because of gas, we need a lot of heat transfer area using fin, something like that. So that this is a counterflow. First of all, if you look at this is a counterflow, and we use a heat pipe, as many as a heat pipe, and we more or less we understand the heat pipe, and finned. Yes,
You said you were gonna discuss midterm two when you got done with break. Is that still happening?
yeah, this is the one.
Oh, this is for midterm two?
Yeah.
Okay. Thank you.
Okay. Yeah, this is midterm too. So listen carefully, and you can raise a question. I think a little bit here. The fin is complicated. We never dealt with this type of fins. It's not rectangular. It's not radial fins. So as long as we can figure out how to handle the fin, otherwise we can handle this. Heat transfer coefficient, friction factor, and the heat pipe, hot and cold fluid, and dimensions given, L1, L2, L3. The L2 and 3 is the same for cold because of gas. L4 maybe or same or different L1, the lengths, anyhow, even. And then adiabatic lengths, okay? So this type, the something total number of tube is number of rows, and then number of tube per rows. You know what I mean? There is So whatever, define the number of rows and how many tubes, then multiply, yeah, something like that. And number of fins is number of pitch, you know, relationship. So that I can figure out the fin pitch using number of fins per unit area. And then again, total heat transfer is primary and the fin. So exactly same idea, primary, I can figure out. Delta is the thickness of the fin. And then fin also, I can figure out 3 terms. I don't have to really, and then cross flow area also I figure out. It takes time, but you can look at it. So we can figure out the cross flow area and then tube pitch. And this is a pitch of C. I defined it. Okay. So also correlations, I found Jacob factor, Corbin factor, and then I try to verify with the experiment. Not really good, but what can you do? This is the one of the best correlation and the experiment for Corbin factor. So there's some uncertainty, but this is the best. There's some uncertainty increases, and a friction factor. Some group of experiment, some is a good agreement, others is not. There's also uncertainty. I was not able to completely agreement. Okay, that's the yeah. It's so even though there is uncertainty, we can, something is better than nothing, we can calculate. Okay, so maybe if you calculate, maybe you have to put some uncertainty. I don't know, we can estimate 10% uncertainty exists. So pressure drop also we can calculate. And fin efficiency is, this is my idea. It's a plate, but if you look at the pentagonal, hexagonal, not the pentagon, hexagonal, assuming there is no heat transfer, no, then it is something like hexagonal, and then hexagonal assuming circular, exactly same area must be the same. Otherwise, I look at it, numerical computation based on, we cannot do that. So analytically, assuming hexagonal and the circular convert, well, then there is no heat transfer, then it's a good assumption. If it is everything same, there might be no heat transfer between, because everything is the same, symmetry. So then we're gonna use a radial fin. Wow. We're gonna use a radial fin and efficiency. You can calculate the hydraulic equivalent diameter and overall efficiency. Everything you can do that. Single fin efficiency, overall efficiency, as long as, and area, single fin and total, and then heat pipe. Still, you can use this concept, resistance. thermal resistance. Pipe and the wick are the same. And what is a type of wick? Type of wick is they use a groove, micro grooved tube. Have we discussed the groove? Yes. Once it's a groove, then it works. The surface tension and then the same, it works. So there's no wick, the groove is okay. And we can use the concept. And now we use cross flow. No, not the cross flow, counter flow, NTU and the CL and the UA exactly. Well, actually total heat pipe divided by number of tube turns out a little. So I showed. And then CL, NTU, you can calculate the effectiveness. Very interesting. No matter how, as long as it's counter flow, you can use a counter flow NTU. That's the powerful. So that once you have that, then you can heat transfer calculate and the pressure drop also. So using the effectiveness compared with some experiment analytical is a good agreement. Okay, this is my work. So for 16 problem, that's midterm. Midterm 2 due next is 27 by 4 p.m. This is a take-home exam. So you have 2, midterm and homework, but take home. Okay, so you have to really work on that. I will announce it and post it, midterm, not yet. So we have midterm and the homework this week. You're gonna be busy. Question?
So just to clarify, the homework is problem 413, and then
Yes.
the midterm is problem 416.
Correct.
Okay, thank you.
Yeah. So the challenging is for 13. There are example. You can go over maybe similar procedure with the example, but for 16, there's no example. For 16, you have to use your knowledge and previous information to figure out the fin efficiency, overall efficiency, everything by yourself. So for 16 is challenging. Heat pipe heat exchanger. And obviously, this is very interesting. What would we, well, we can improve. I just roughly made it. So it's not the best effectiveness. No, we can work on that.
We can use the effective NTU method then?
Yes.
Is this is still cross flow, correct?
No cross flow.
It's not cross flow?
No. Look at that. Is this a cross flow or something?
Oh, no.
What is
I
that?
see.
What is that? You tell me.
Well, we have hot on one. It's like two systems put
Counterflow.
together.
Say again?
Counterflow?
Yes. You can use a counterflow. Okay?
Okay.
Any other question? I'm done.
Will we be meeting for class next week then?
No. Oh,
Okay.
No, next week is there's no class.
Okay, so we just have to turn in 416 before 4 o'clock next week, and then
No,
have
I'm
our
gonna
exam.
change. I'm gonna change it to 7 p.m. due.
Okay, and that's all we have for our exam next week.
Yeah,
Okay.
no class, no class.
Okay, thank you.
Yeah, I will announce it. Okay, so no class next week, exam, but the take-home exam, I mean, I will give you plenty time.
Will you be posting this lecture?
Yes. Oh, okay.
Just went fast. It was really fast through some of it. and
Okay, I will do it. I will do it. I will post
All right.
the lecture.
Thank you. Bye.
Okay. Any other question? Bye bye.